This is a video to help you understand how to use Faraday's laws. It's chapter 9.3. These are the slides which are numbered down here, so if you pause it you can see what's on this video. Okay, so we're looking first at the stoichiometry relationship between the mass of the oxidizing agent and the mass of the reducing agent in a electrolytic reaction. So just a quick reminder, if you've got a galvanic cell, you can look at the anode. That's the zinc is losing the electrons. You can tell this because the electrons are going in this direction. So the zinc metal's losing electrons and the copper ions are gaining the electrons. So the zinc's undergoing oxidation, the copper's undergoing reduction. So we call the zinc the reducing agent. It's undergoing oxidation. It's the reducing agent. And we call the copper ions the oxidizing agent because they're undergoing reduction, so it's the opposite names. The chemical which is undergoing oxidation is the anode, an oil rig, cat. So this is the negative electrode, this is the positive electrode. So this is a galvanic cell. For oxidation, this is losing the electrons. So what would happen to the zinc metal after a period of time? And these ions are coming over here and being turned into atoms. So what would happen to the copper electrode over time? So the zinc would get holes in it because it's being turned into zinc ions. So this metal would start to fall apart and this metal would start to build up because extra copper atoms are being added. Decrease in mass and increase in mass. So we know there's 2 electrons lost, 2 electrons gained, so it's a 1-to-1 ratio. So if 10 grams of zinc was lost here and converted to copper ions, what mass of copper would form? So if I ask this question in a class, there's always somebody that yells out 10 grams of copper before they think about it. So we know from stoichiometry that you can't go from the mass of one thing to the mass of something else directly. It's not 10 grams of this to 10 grams of that because the size of atoms are different. So a zinc atom compared to a copper atom, they're different sizes, so they'll have different masses. So we have to convert the mass to number of moles before we could relate it. So if you've got 10 grams of zinc, you've got 0.15 mole. It's a 1-to-1 relationship, so you've got 0.15 mole of copper being formed. Copper atoms are slightly smaller atoms, so the mass of a mole is less. So if you have 10 grams of zinc being lost, you would form 9.7 grams of copper because they're slightly smaller atoms. Okay, so this is a galvanic cell and we're relating mass to mass. So we know that we can relate the mass of this to the mass of that being formed stoichiometrically, but it's the electrons that are actually forming this. So is there some way of relating the electrons being moved across here so that we could work out how much copper we would make if we knew how many electrons were coming in to form the copper? So can we relate the mass? We could relate the mass of copper formed to the number of moles of electrons. So we need some way of measuring the electrons, which leads us into this electrolytic chapter. Alright, so there's 2 laws, Faraday's laws. He defined these laws. So the first one is that we can relate the mass of the chemical that we're looking at, for example copper, to the amount of electrons, and we're going to call the electrons charge and call them Q. So it's proportional. The higher the charge, the more electrons, the higher the mass that you form. So that's his first law, that those 2 go together. So you need to remember these steps off by heart so that you can, if you're given the charge, the amount of electrons, you could work out the mass of the chemical that's going to form. You also need to know these steps off by heart so that if you're given the mass, you could work out the charge that must have been used. So you could work out the charge is going to be made up of 2 parts, the current of electrons and the time that that current was flowing. So if you're given the mass, you need to be able to use these backwards to work out maybe the current that was used to form that mass, or the time that it took to form that mass. So you need to know these equations backwards and forwards, so you need to know them off by heart. So this is a good slide to come back to remember them. So we're going to go through these individually. So Q is the charge. Okay, so the first equation that we use to work out the mass deposited is Q. So Q is the charge. So Q equals IT. I is the current in amps. So if you're given milliamps or something, you have to convert it to amps. And T is the time taken. So the current is looking at how many electrons are being transferred, and obviously the longer that you do that, the more electrons will be transferred. So you have to take account in the current and the time. The time's in seconds. When you multiply these two together, you get a new unit, which is looking at charge, the amount of electrons, and it's coulombs, C. So to convert whatever time you're given to seconds, there's 60 seconds in a minute if you're given minutes, and there's 60 minutes in an hour, and there's 24 hours in a day. So to work out how many seconds in an hour, each minute has 60. If you've got 60 minutes, it's 60 lots of 60, so 3,600 seconds in an hour. If you're doing there's 24 hours in a day, so you'd have this 24 lots of that, so 24 times that would be 86,400 seconds if you were doing it for a whole day. So however much time you're given, you just multiply accordingly to find out the number of seconds. So once you've got Q, the amount of charge, this coulombs, when you multiply them together, doesn't really tell you how much electrons. It's just a whole new unit. So you need to know how many coulombs, how does that relate to the amount of electrons. So 96,500 coulombs is the number of coulombs you would need to have 1 mole of electrons. So if you had 96,500, you would have 1 whole mole of electrons would have been delivered. This is Faraday's number, 96,500 coulombs. So if you're told that you have a Faraday of charge being delivered, then you have 96,500 coulombs, or you can just say I've got 1 mole of electrons. So you wouldn't have to work this equation out if you were told you had a Faraday of charge. You just know that you had 1 mole of electrons already. So this relationship here is useful if you want to convert one to the other. Okay, so once you turn your current and time into coulombs, then you divide it by 96,500 and you'll have however many number of mole of electrons. So to show you how this helps knowing the electron mole, instead of relating the number of mole of copper that you would have deposited compared to the number of mole stoichiometrically to the number of mole of zinc, you're using your half equation to look at how many mole of copper would I have compared to the number of mole of electrons. So it's still a stoichiometric relationship, but it's with electrons rather than the other component that's losing the electrons. So you can't go any further than the mole of electrons. You can't work this out unless you've got the half equation. So at this point you need to write the half equation. So if you wanted to know how much metal you would deposit, you need to relate it to the number of mole of electron that you've just worked out. So it's a half, 1 to 2. So if we had found already from our charge, coulombs, that you had 4.3 moles of electrons, what mass of copper, you'd find that you have 2 and 2.15 mole. So you're doing stoichiometry with electrons, and then you can work out the mass just using this equation. So we've kind of quickly worked through those 5 steps. So this is the first example. So if you write this out, highlight the information that's useful. So we've got a copper plating, so it's electrolysis, the steady current of 30 amps for 20 minutes. The question is, what mass of copper is plated on the object? So when you're reading your questions, can you write around the question what type of information? So use the symbol from your equations. So you've got current here, amps, and you've got time. So you want your time in seconds. In this case, your time's in minutes. And the questions are asking you to find the mass of copper. So you can see you've got current and time. You can find Q. So you're just working through all your steps in the normal way that you would have remembered. So step 1, you're finding Q, the amount of charge. Q equals IT. You've got 30 amps, and you need to turn your 20 minutes into seconds. So 60 seconds a minute. So you've got 36,000 coulombs. You'll get used to Q being a large number. If it's not a large number, you're doing something wrong. So 36,000 C. So that doesn't really tell us anything about electrons, so you need to divide that by 96,500. You'll get that the number of mole is 0.373 mole of electrons that you've delivered. So the third step, you need to know what's the ratio between electrons and copper. So it's a 2 to 1. So you put what you want on the top, so you're trying to find your copper. You've been given your electrons. So remember, these numbers go with 2 to electrons. So basically it's a half. However many electrons you've got, you're only going to make half the number of moles of copper. So the number of moles of copper that you're making is 0.187. So the last step, to find the mass, you just use this equation, and you've got 11.8 grams. So if you're given the current and time, you can work out the mass of copper. So next question, how long does it take to deposit 50 grams of copper at the cathode of a plating cell with an 8 amp current? So write down, before you start doing anything, you need to know these equations off by heart. So I would recommend on the exam that you just write them quickly down so you can see how you're trying to tackle. Just remember them in order. Q equals IT, number of moles of electrons is Q on 96,500. Then you use your half equation, your ratio electrons to whatever it is that you're finding the number of mole of, and then you can use whatever other equation you need. In this case, we're looking at mass. Okay, so put your equations down and then see how they help you tackle the question. So the question, if you go through, the question's asking you for how long, and you've been given the mass. You've also been given the current. So you want how long, but you've been given the mass. So you know this already, and you're trying to find this, and you've been given this. So you can see that if you're starting here, you know this already, and you want to find T, that you're working through this backwards. You're going from the mass of the copper to the number of moles of the copper, using your ratio to find the number of moles of electrons. Then you find Q, and then you're going to rearrange Q to find T. So you're using this equation backwards now. Once you've got the mass of copper, then you can find the number of moles. You use your half equation. You've got the mass, number of moles of copper. Use your half equation to find the number of moles of electrons. It's around the other way from the previous example. Then once you know the number of moles of electrons, you rearrange that equation. Instead of dividing it by 96,000, you multiply it by 96,000 to get Q, and then you rearrange Q equals IT to find T. I should have rearranged this too. N equals mass of molar mass. Okay. Whoops. So first step, we want to find the number of moles of copper. So it's 0.787, and then we have to go from the number of moles of copper to the number of moles of electrons, so we know it's a 1 to 2 relationship. So you always have to write your half equation down. You put what you want on the top. Because you're going backwards, you want to find the number of moles of electrons this time. So it's a 2-on-1 relationship, so you're multiplying the copper by 2 to get 1.7. Then you're rearranging, we've got the number of moles of electrons, so you multiply that by 96,500 to get Q. It's 1,000. Remember that your coulombs are going to be a large number. So you know Q, you know the current from the question. So you rearrange this to find T. So multiply it on this side, take it over the other side and divide it. So you've got 19,000 seconds. So must have a look at the question and see if the question wants your time in seconds. If it wants it in hours, then there's 60 seconds in a minute, 60 minutes in an hour. You'd have to divide that by 3,600 and you get 5.28 hours, so 0.28 of an hour. So you could write 5 hours and then 0.28 of an hour, 0.28 of 3,600. You could keep this in seconds if you wanted to. Okay, so this is a good summary of Faraday's laws, the first laws. So we've been looking at Q and working our way all the way down here to find the mass. So these are the 5 steps. Q equals IT, and then once you find Q, you're dividing it by 96,500 to find the number of moles of electrons. Using your half equations, you're finding the number of moles of whatever it is that you're looking at, and then you can find the mass. So these half equations, so far these are both reduction reactions. So for this one, could be the mass of metal. So you've got a metal ion, you're adding electrons to make some sort of metal coating on the cathode. But you could also be producing, if you're adding electrons to something like chlorine gas, you could be making chlorine ions at the cathode. So your half equation can be different depending on what it is that you're forming. As well as that, we've been using the number of moles of electrons that we're relating it to the number of moles of metal to find the mass of the metal, but you could be relating the number of moles of whatever it is that you're forming to, like if you're forming a gas, you could find, once you know the number of moles, you could find, then use PV equals nRT to find the volume of the gas, or you could use SLC, the equation for number of moles is V on Vm, to find the volume of gas. So, or you, instead of having these reactions written as reduction reactions, you could write them back around the other way and work out what's going on at the anode. So oxidation reactions. So you could, if you were looking at how many ions were being formed at the anode when you removed electrons, you could work out the concentration, the new concentration of the solution. So you can interpret these half equations and what you find. You can find lots of different things once you find the number of moles. And then, as well as looking at these 5 equations in this direction, we also went and worked back the other way, so that if we were given the mass, we could work out the current that it took to form that mass, or the time that it took to form that mass. So this is kind of a good overall summary to have on the wall, perhaps. Later on, we're going to add the voltage to your current and time. So if you know the energy, the volts are like the energy of the electrons that are being transferred. If you know the voltage of those electrons, then VIT will give you Q, and you've already had an equation with Q. Q equals mc, change in T. So Q is joules. So if you know the voltage of the electrons that are being transferred, you could work out how many joules of energy you are adding to that system, or how many joules of energy it took to add those electrons. So V equals IT, or V also equals Q. So you could be, instead of having to work out Q, we've already looked at this. If you, instead of having the current and the time to work out Q and then to work out the number of moles of electrons, if you're given a certain number of Faraday, so if you said I had 1 Faraday, that already means you have 1 mole of electron. So if you know the number of moles, if you're given a certain number of Faraday, that you can work out the number of moles of electron, 1 Faraday and 1 mole of electron, you multiply it by 96,500 and you would get Q. So you don't need to have the current and the time to get Q if you have the number of moles, the number of Faraday. So this is useful too, and it would be useful too if you knew how many Faraday, you could find Q. If you knew the voltage, you could work out the amount of energy. So there's lots of ways of tackling these questions. Okay, so Faraday's second law is basically an extension of the first law. It's just that instead of relating Q to the mass, that they're proportional, the charge goes up, the mass goes up, it goes up in proportion to the number of moles of electrons. So it will be different depending on the charge. So the number of moles of electrons that you need. So if it was silver that you put the electrons through, you would have a different number of mole of silver being produced than if it was copper or chromium, because the number of moles of electrons, it's a 1-to-1 relationship for silver. So for every 2 moles of electrons you would only make 1 mole of copper. 3 moles of electrons you would need for 1 mole of chromium. So it's another way of looking at this. So that was looking at how many amount of metal that you would form depending on charge here. Another way of looking at it is how many, this is around the other way, this is the amount of metal. So the x-axis here could be moles of electrons. So for every 1 mole of electron for silver, you would make 1 mole of silver metal. 2 moles of electrons, you would make 2 moles of silver, etc. This is written, instead of saying 1 mole of electron, it could say 1 Faraday, 2 Faradays, 3 Faradays, or 96,500. So it's a 1-to-1 for silver, but if you have 1 mole of electron, you only make half a mole of copper. Half a mole. So 1 mole of electron, you only make half a mole of copper and 1/3 of a mole of chromium. Okay, so if you put the same, it's good to look at the same number of mole of electron. How many mole of each of the metals would you form? If you put 3, so your relationship, I've written the ratio, instead of number of mole of chromium to the number of mole of electron, I've actually written this around this way, so it's 1/3 of a mole. So if you had 3 mole of electron, then you'd get 1/3 of that as chromium. If you had 3 mole of electron, you'd only get half of that as copper. 3 mole of electron, you'd get exactly the same. So I have seen somebody make a mistake where they realized it was a 3 to 2 to 1 ratio, and so they kind of just assumed that you could swap those numbers around, so it would be a 1 to 2 to 3 number of moles that you would produce. It's correct for 1 and 3, but you can see half of 3 moles is 1.5, not 2. So you really need to write these out and do calculations. Alright, this is a question that uses that understanding. So it's asking you to find the oxidation number of the gold ions. You remember the charge on an ion is the same number as the oxidation number. So if you find the charge on the ion, you'll find the oxidation number. Whenever you're given some information, it's good to look at it and see if you can work out, what kind of equations could I potentially use. Sometimes this is a red herring though. They'll give you information that you don't even need to use, but it's always good to have a look. So you've got 4 amps, which is I, current. If you write down the symbols, it'll help you work out what equation you need. You've got time in minutes, and you need to turn it into seconds. So therefore, you've got I and T. You could work out Q if you had to. Density. The density equation is the mass of whatever chemical it is in the volume of the same chemical. So the mass of the gold divided by the volume of the gold that the gold takes up will tell you the density. It looks very similar to a concentration equation, the mass, but the concentration equation is the mass of one chemical in the volume of something else. These are both referring to exactly the same thing. The mass of the gold and the volume of the gold gives you the density. You can see up here you've got the volume of gold. So you've got the density, you've got this number, and you've got this number. So therefore, if you rearrange that equation, you'd be able to find the mass of gold that you had. So already you can see, knowing the equations that we have, those 5 equations that we use, you've got the first one, Q, and normally you would work your way down to work out the mass, so you've got the last one. So you can see that you could work out the first step and the last step. And you're trying to find the oxidation number. So if you put all of your equations in order, you've got Q, you can work out Q, and you've got the mass, so you can work out the number of moles. And the question's asking you to basically work out the ratio. So if we look, we want the oxidation number. The oxidation number is the same as the charge on an ion, so we want to know what this X is. So this X is the same as the mole ratio, the mole ratio number with electrons. So if this was 1 plus, you would have 1 electron, 2 plus, 2 electrons, 3 plus, 3 electrons. So normally we use this 1 to 3 ratio when once we've got the number of moles of the electrons, then we can use the ratio to find the number of moles of what it's forming. So normally we use these numbers, but this time we're going to find the number. So we're using the ratio to find that, which means we need to know the number of moles of electrons and the number of moles of gold. So we're working from both ends for this particular equation. We're using IT to find Q, and then turning Q into the number of moles of electrons, and from the other end we're using the volume of the gold, the density of gold, to find the mass, and then we turn that into the number of moles of gold. So we've got our 2 parts of our ratio here. And then if we relate those, the number of moles of the electrons, number of moles of gold, and work out what the ratio is, it'll be a 1 to 1 or a 2 to 1. This will be twice the size of that number, or it'll be the same size as that number, or it'll be 3 times the size as that number. So if we can work out the number of moles of electrons, number of moles of gold, we'll be able to work out the ratio, so the charge. So let's do that. We've got 4 amps, and our time is 53.25 seconds. So if we multiply that by that, we get 4,260 coulombs. When you divide it by 96,500, that coulombs becomes moles. I probably should have made that significant figures. So we've got 3 significant figures here, 3 here and 3 here, 4 here. So I should have cut that down to 3. So it should be 0.0441. So that's our first part of our ratio, and then the questions are helping you work out the second thing to do. So you need to find the amount of gold. So you rearrange the density equation to find the mass of the gold, and then you can use that equation to find the number of moles of the gold. So now we've got our number of moles of electrons and our number of moles of gold. So if we divide those, they're exactly the same number, so we can see that X was 1. This is a 1-to-1 relationship. So the charge on the gold is 1, so the oxidation number is 1. If the charge was 2 plus, then this number here, the number of moles of electrons you would need, would have to be double, 0.0882. The number is 1. Alright, this is another exam question. So the mass deposited for a set number of electrons depends on the number of mole required, so Faraday's second law. So we've got 5 litre volumes of 1 molar potassium nitrate, 1 molar silver nitrate and 1 molar copper nitrate. So basically the same concentrations, so the same number of mole of potassium, silver and copper are placed in 3 separate over a period of 30 minutes. 96,500 coulombs of electric charge are placed through each solution. Which of the 3 alternatives indicate the amount in mole of metal deposited at the cathode in each cell? So you can see if we've got the same concentration and the same volume for each of them, then we will have the same number of mole of each of them. So the thing that's making the difference between each of them will be the charge on the ion. So it's Faraday's second law. I've highlighted here, you can see solution. So when you have a look at the ratios, hopefully after the beginning of chapter 9, alarm bells should be ringing. Which one of these should alarm bells be ringing for before I show you the answer? The fact that it's a solution should give you a bit of a warning. Okay, so there's water. If it's a solution and you're doing electrolysis, water is a stronger oxidizing agent than all of these metals. So if you're adding electrons, the water will get the electrons first and turn into hydrogen and hydroxide. So you will never get any of these metals formed. So because potassium is one of them, potassium would not react. So you really need to, with electrolytic cells, really need to be careful with water. Always be on the lookout for water. So you don't need to worry about anything that has potassium metal being formed, because no potassium metal would be formed. Hydrogen would be formed instead. Alright, so now it narrows it down to these two. You don't need to calculate Q, so it's got 30 minutes and you might be hunting around trying to work out, what do I do if I don't have the amps? How do I work this out? How do I find out the number of moles of electrons? You don't have to. If it gives you coulombs, you remember 96,500 is the magic number for coulombs. If you have 96,500, then you have a Faraday of charge, you have a mole of electrons. Each of these things equals each other. So it's telling you already. So the 30 minutes is just to throw you off a bit. It's told you you've got a mole of electrons. So you just need to relate the mole of electrons to the half equations. So remember, silver is 1 plus, so you need 1 mole of electrons, and copper is 2 plus. So to make 1 mole of copper, you would need 2 mole of electrons. So if you've got 1 mole of electrons, then you're going to make 1 mole of silver. And clearly, you don't even have to know that, because both of the examples have 1 mole. So it's the copper that we need to be working out. So you can see it's a 1 to 2, so does that mean you double the number of moles of electrons, or you halve the number of moles of electrons that you're given? So remember to set up your ratio. What you want on the top, what you want is the number of moles of copper, what you've got, electrons, so it's a 1 to 2. So basically the number of moles of copper that you would form is half the number of moles of electrons you've got, so it's 0.5.